Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 9, Lesson 6, Solving Systems of Linear and Quadratic Equations. So if you think back to pre-algebra, we have solved systems of equations before, two linear equations using substitution or elimination. We can do the same thing if one of those equations is a quadratic equation. For the model and discuss, we have this diagram, this archway. An architect is designing this archway for a building that has a 9-foot ceiling. So up here at my vertex, let's label some points. If this is a 9-foot ceiling, I know it's something comma 9, right? And I can see that up to where the arch begins is only 7 feet. So that means from here to here, this distance is going to be 2 feet, okay? And then we have a width of the archway is 5 feet. We want to find a quadratic model for the arches if the highest point of the arch touches the ceiling. So we already have that point. That's the maximum, something comma 9. Well, where's the x-intercept going to be? Halfway in between 5, right? It's going to be right in the middle. It's going to be 2.5 comma 9. There's the vertex. Can we label the other points? Well, this point is going to be, if this is 0, if this point is 0 comma 0, this point here is 5 feet over. That's going to be 5 comma 0, okay? And that means this point up here is going to be 5 comma 7. And this point here, we can label this one too. It'd be 0 comma 7. So now we have these points of our parabola. This is helpful because this will help us come up with our quadratic equation. What's the vertex? 2.5 comma 9. That means h is 2.5 and k is 9. So remember how we've done this before. We have our function a times x minus h squared plus k. So if we write it in vertex form, we can come up with our quadratic equation. We know our point, our vertex, is at opposite h, which is negative 2.5, and k is 9. We don't know a yet. How can we solve for a? Do you remember how we did this? Well, we can take any point that we know, and plug that in. So let's take the point 5 comma 7. That means my output is 7 equals a times x is 5 minus 2.5 squared plus 9. And now I just solve for a. And if I do the calculations, I'm not going to do it all, but we've done this before. If we solve for a would equal negative 0.32. And then we can plug that into our quadratic formula. It would be f of x equals negative 0.32. Does that make sense? It's a downward parabola. That is correct. Times x minus h, which is 2.5, squared plus 9. Okay, so here's our equation for the quadratic formula for this archway. Part B, describe how to change the model so that the highest point of the arch does not touch the ceiling. Well, then in that case, this constant would be smaller, right? It would be like 8 or 8.5, something like that. So that would mean then that value would be different. A would also be different because the parabola would then be a little bit wider. It wouldn't go up as high. It wouldn't be as stretched out. So how is solving linear quadratic systems of equations similar to and different from solving systems of linear equations that we did in pre-algebra? Let's take a look at it. If we have a linear quadratic system, that just means one equation in the system is linear and one is quadratic where we have an x squared term. That's it. And we're still looking for solutions or where those two are the same value, where they intersect. So how they're similar, a solution to this system would be where those two lines would meet, where they cross, where the graphs would intersect. So depending on where that linear equation is graphed, they could never intersect or have no solutions. They could intersect at exactly one place, only once, or they could intersect in two places and have two possible solutions. So the difference is we cannot have infinite solutions as we could with a linear system. How many solutions does this system of equations at the right have? So this is a linear equation. It's just going through the origin, okay? And so they're both going through the origin. We could draw it if we know our parent functions. So x squared is just going to be going through the origin with a slope of 1. And my parabola is going to be going through the origin also. See if I can get it down there. Can't really see it, but they're going to be both intersecting at the origin, and then when the parabola goes back up, it will intersect again. So there will have two solutions at the origin, and then where they intersect, which in this case will be at 1, 1. How can we use graphs to find the solutions? Well, just like we did with two linear equations, we can graph them and find the intersect. So you would type these into y equals on your graphing calculator, and then you would do calculate second trace. To calculate the intersect. And you could see that this graph would have two solutions, and you can find those two solutions, those ordered pairs, using our graphing calculator. So if we were to check that then, our solution, if x is -2, if I plug that into my solution, it would make both equations true. And if I plugged in my other solution, the x value for my other solution, it would make both equations true. They would be the same thing. They would get the same y value, the same output. Try it number 2. Rewrite this as a system of equations and graph to solve. So if it's going to be a system, if they're equal to each other, that's what we're looking for when the solutions are the same. So it's just give them both a y. So y equals x squared plus 1 is my first equation, and y equals x plus 3 is my linear equation. And then we're going to type that into the graphing calculator. So on your graphing calculator, type in your first equation, x squared plus 1, and your second equation is x plus 3. And we're going to second trace to calculate the intersect. We can see there's going to be two of them, so let's move our cursor to the left of our intersect, hit enter, and move the cursor to the second curve, hit enter. So there's one intersection at -1, 2. And let's do the other intersect. So second trace, calculate the intersect. I'm going to move it over here. Here's my first curve, my second curve, intersect. My second intersection is at 2, 5. So two solutions for this system. For part B, again, you're finding the solution or where they're equal to each other, so just give them both a y. Y equals -0.5x squared plus 5. Notice I wrote it in standard form. And the other equation would be y equals -0.5x plus 2. Let's use our graphing calculator to find the points of intersection. So under y equals, type in the first equation, -0.5x squared plus 5, and then type in the other one, -0.5x plus 2. And we're going to hit second trace to find the intersects. We can see there's going to be 2, so we're going to do this twice. Move my cursor down. There's my second curve. Hit enter. Okay, first point of intersection is -2, 3. Let's do it again. Second trace. Find the intersect. I'm going to move my cursor closer to this point of intersection. Hit enter. There's my second curve. Hit enter again. My second solution is at +3. Example 3, solving systems of equations using elimination. So we did this in pre-algebra. We want to eliminate one of the variables. We can change one of the equations and write an equivalent equation by multiplying the whole thing by a constant. So if I want to eliminate the y variables, they need to have the same coefficient but opposite sign. So I'm going to multiply this whole second equation by -1. That gives me a new equivalent equation for my linear equation. It's going to now become -y equals -2x plus 4. And then we can add those together. So if we add those two equations together, my y's will cancel. X squared doesn't have anything, so we're going to bring it down. X squared, -6 plus -2 is -8x's. 8 plus 4 is +12. So then we have our new quadratic equation, and we can factor that and use the zero product property. So factors of 12 that add up to -8, be -6 and -2. Split the binomials, set them both equal to 0, and then solve for x. We would get our solutions, x equals 6 and x equals 2. Remember, these are just the x coordinates. The x values were the inputs for where the graphs would intersect. This does not give you the output values. It doesn't give you the second coordinate for that point if you were graphing. We could find the y values by plugging x equals 6 into the equations and solving for y. So you could find the ordered pairs by plugging each of those solutions back into one of the equations. So I'll show you. Let's plug it into the second one. Y equals 2 times 6 minus 4. So y equals 8. So one ordered pair would be 6, 8. And the other one, if I plugged in 2, y equals 2 times 2 minus 4. So y equals 0. And so my next ordered pair where they intersect would be 2, 0. So you could find the whole coordinate, the ordered pair for the point of intersection. Try it number 3, use elimination to solve each system of equations. So for part A, I need to eliminate the y variables. I'm going to multiply one of these equations by -1, so they'll cancel out. I'm going to rewrite the system. -y equals no x squared term. I'm going to have a positive x and a -4. Y equals x squared, no linear term, minus 2. So add those two equations together. My y's cancel, bring down the x squared, and I have a positive x, and then I have a -6. And now I can factor that. Factors of -6, that will give me +1. It should be -2 and +3. Using the zero product property, split the binomials. I know x is going to be 2, or x is going to be -3. Now I need to get the y coordinate, so now I'm going to plug in x equals 2 into one of the equations. So let's just do the first one. It's simpler. Y equals the opposite of 2 plus 4, and that would equal -2 plus 4, which would be 2. So one coordinate is going to be 2, 2. Okay, let's do the second one. If I plug in 3, y equals the opposite of, plug in -3 plus 4. The opposite of -3 is +3 plus 4 is 7. So my next ordered pair would be -3, +7. All right, let's do part B. Since I have this negative x squared term, I'm going to multiply that one by -1 so I can get rid of that negative coefficient in front of the quadratic term. Let's rewrite the system. So I'm going to have -y equals +x squared minus 4x minus 2. And my linear equation stays the same. It's a +2 and a -x. Notice I lined up all of my like terms. So I can rearrange the linear equation so I can line up my terms. Add these two equations together. My y's cancel. I have x squared minus 5x plus 0. I can factor out an x, and then I'll have x minus 5. It equals 0. Okay, since it equals 0, I can split the binomial. So x will equal 0 or x will equal +5. Now I have to find the y coordinate, so I'm going to plug in those x values to the equation. So y equals 2 minus 0. My y coordinate is going to be 2. So I have 0, 2 for my first point of intersection. Now I'm going to plug in 5. So y equals 2 minus 5. Y is going to equal -3. So my second coordinate for the point of intersection is 5, -3. Those are my 2 points of intersection, my 2 solutions. How would we use a system of linear quadratic equations in the real world? Here we have a phone company launching the sale of 2 phones in the same week. The phone on the right is an upgraded version of the other phone, and you can see the projected sales are represented by that linear equation. The other phone the sales are represented by this quadratic equation. During what weeks are the sales projected to be the same for both phones? So now we're looking for our point of intersection, our solution for this system. I'm going to show you substitution, the substitution method. Since we're looking for where they are equal to the same price, they're just going to be equal to each other. So I'm going to rewrite this system so the equations are equal to each other, and then we're just going to solve. Okay, move the 20x to the other side. Now I'm going to have 0 equals negative 2x squared plus 40x, and we can factor. We can factor out a negative 2x. So I'm going to get x minus 20 as my factored form. That equals 0, so we can use the zero product property, split the binomials. Negative 2x equals 0, so that means x equals 0. Well, can I have 0 number of weeks? No, we're not going to use that. So our next solution would be the one we're going to utilize. X would also equal positive 20. So I can use that as my input to find the output or the projected sales for each model. So if we plug that in, 20 times x is going to equal 400. So for the first equation, the phone on the right, we will get a projected sales of 400,000. And if we plug it into the second, we should get the same value because that's when they're equal to each other. So we know that they're going to be making 400,000 at this point when x equals 20. So after 20 weeks, they will be making 400,000 phones. Try it number 4. Could you have used elimination or graphing? Yes, we could have. We could have used either method to solve. You can use any of those, graphing, elimination, or substitution. Just choose the one that is most efficient. So, for example, if you have an equation written in standard form and then another written in linear equation form, I would probably use substitution because then I could just take my linear equation and substitute that in and set the two equal to each other. But sometimes it might be difficult to factor that way. You could also use graphing if you have a graphing calculator, find the points of intersection. Made it to the concept summary for solving linear and quadratic systems of equations. So just remember you can use either of these methods, elimination, substitution, or graphing, and we can have 0 solutions, 1 solution, or 2 solutions depending on how many places that linear equation and that parabola intersect. They could not intersect, they could have 1 point of intersection, or they could have 2 points of intersection. If you have any questions, put them in the comments. Make sure to like and subscribe, and come back for topic 10.